sciences. Ladies and gentlemen, welcome to the presentation of the solution provided by the University of Belgrade, Faculty of Organizational Sciences. My name is Darko Damjanovic. I'm an undergraduate student of Operations Management, and beside me the team members are Andrijana Bačević, Nemanja Vilimonović, and Igor Dabić, all master students of Business Analytics, and Jakov Petrović, master student of Information Technologies. We all hope what you're about to hear from us today meets your expectations. Before we start, a short introduction to today's presentation. At the very beginning, there will be a few words about problem statements and framework, what we have understood to be an object and objective of the problem. Furthermore, there will be some words about the data, what we have done with it, and discovered later to help us with our work. Third will be methodology, where our team leader will explain heuristic we have used for generating the solution, called variable neighborhood search. And after that, solution analysis with all the fine tables and, let's say, additional information about our solution and information about some interesting experiments we have conducted. At the very end, short conclusion will be provided with main aspects of our work once again and main points where our solution outperformed the benchmark. In order to make an adequate portfolio, which can be defined as a mixture of assets, one must strive for a balance between risk and return. And of course, every manager wants that adequate portfolio to be an optimal one. Framework used for solving this problem is the following. A big set of data was provided with lots of dates they are situated in. The main idea was to generate a set of weights. Then we can understand that one as picking up specific assets we're interested in investing in, then to store those weights and to repeat the iteration over every single period of time there is. At the end, we have portfolios we will invest in for every single period of time. This framework, capable of the optimization, must be introduced to a set of constraints. They form feasible area or an area where we search for an optimal solution. And this kind of optimization iteration is conducted via, as previously said, heuristics called variable neighborhood search. From this point on, my colleague Jakov will explain what we have done with the data.
Certain time we've spent in extracting general information about time series, risk models, visualizing benchmark activity during period, and later comparing it to our solution. Also, we've visualized 4-weekly return, and it had a shape of bell curve. So, during 10-year horizon, more than 700 unique cells were identified. Those are related to companies that used to trade with multiple types of stocks, change their industry branches, or even disappear from the list. Benchmark kept portfolio fully invested in every stock, having average number of 264 settles per period that weighted less than 0.1% each. Missing entrances found in covariance matrices are treated as proposed in the task, 0.5 for diagonal elements and 0 for the other one. One of the interesting things about data also concerns risk models. Covariance matrices have been visualized here, and we decided to present those from the first and last period. In the first row, settles are sorted by industry sector. It has been noticed that assets within same or similar categories have higher covariance. It's the case with energy sector over there. Okay, I'll use this. Energy sector over there in the first period, for example, or IT and telecommunication sector, while in the last period we see that IT is pretty much related to, all of the branches and also within IT. Diversifying portfolio by industry sector could probably lower down the risk significantly, which cannot be completely claimed for MCAPQ since we don't see such a strong patterns as in the first case. So having in mind that real data can be 20 or 30 times larger in scale, our charming team leader, Andrijana, will explain what has been done in order to generate solution.
Okay, regarding larger scale data and existence of many additional constraints, it is decided to develop heuristic based on variable neighborhood search, which has in it two rebalance strategies, minor and major one. Major strategy brings total transformation of a portfolio, while a minor one can change it only partially because of the turnover limit. Decision about which strategy will be used is brought upon values of the information ratio. It is calculated from a period of last major rebalance to the present one. So in the first period or in the period after major rebalance, information ratio is said to be a large negative number, and in the next period, minor rebalance is done, where information ratio needs to be updated. While information ratio increases, minor rebalance is done, and where it starts to decrease, then major rebalance is introduced. So, a general idea of the variable neighborhood search heuristics is the following. It is based on local search and systematic change of neighborhood in order to avoid traps of local optimum. There are two crucial phases in this heuristic, and they are shaking and local search. The first phase provides random solution from a neighborhood of current solution, and then it goes through a local search phase. If better solution is generated, then it becomes new current solution. Otherwise, new neighborhood is used in the shaking phase. So there are three procedures for minor rebalance in VNS heuristic, and they are shaking with three different types of neighborhoods, which represent different alpha-beta strategies for adding or removing assets from a portfolio. Then local search phase, which adjusts weights of assets, and because it's the most time-consuming component, one more goal was how to make it as fast as possible, and how we've done it I'll explain later in one example. So for major rebalance, there is one procedure for generating random feasible portfolio, and then it goes through shaking and local search phase in the same manner as it was in minor rebalance. Also, there is one procedure who checks all constraints actively, so adding, deleting, or changing one or more constraints is simple enough. So, speed up of local search I'll explain in a small example with 5 assets. Objective function is given with this equation and is equal to the sum of elements of these two matrices. If only one weight changes, for example, for the asset number 4, only highlighted fields are changing. So if this table is subtracted from the previous one, then the difference is equal to the sum of elements of these two matrices. So, general new value of objective function is now equal to this equation, and it can be calculated in n steps. So this speed up we have made makes exploring higher number of feasible solution possible. So Igor proceeds with presenting our solution.
Thank you, Adriana. Before we go through solution analysis, I would like to mention that we have used the Python programming language because it's well known that it's handy for almost any type of data analysis. Next, it was required that simulation runtime should take up to 3 minutes. So therefore, we came to the idea to run simulation for different times just to see if our heuristic can give us an acceptable solution for shorter execution time. And another thing we were changing during our research was the lambda value, in order to see how our objective function would behave for different lambda values. Here in the table below are presented the main measurements for solutions for 45 seconds and 180 seconds, and for lambdas 1, 5, and 10. Intuitively, it is expected that solution for 180 seconds is always outperforming the solution for 45 seconds because heuristic for 180 seconds has more time to find better solution. And for instance, we can see that Sharpe Ratio and information ratio, Sharpe Ratio, cumulative return are always outperforming the solution for 45 seconds for the same lambda value. Next, using the market cap quintile, we can distinguish the large companies from the small ones, and the assets of the portfolio come from the groups 1 and 2 in more than 85%, which means that the manager has invested more in the larger companies than in the small ones, but also manager follows up the benchmark due to constraints which were given in this problem. Here we have the same overview, but the proportion of assets according to the sectors. We also can notice that the manager follows up the benchmark. The blue one is the portfolio and the green one is the benchmark. Because of the given constraints, which can deviate up to 10% from the benchmark. And the three most interesting fields for Invest was the information technology, financials, and the healthcare in this period. Here we'll be discussing about information ratio, which has to tell us how much excess return is generated of the amount excess risk taken relative to the benchmark. Here we have two lines here. The first one presents the solution for 180 seconds, and another one presents the solution for 45 seconds. We have a nice development through the time for both of these scenarios, a little bit better for 180 seconds, but we have a few drops during this period, for example, in 2008, 2012, and so on, and this will be covered by my colleague Nemanja.
Thank you. Hello all. Okay, in this graph we can see cumulative return through the periods, both for our benchmark and our two solutions. We can see that through the years there has been a constant growth, except a few moments of crisis, like global financial crisis from 2007 to 2009, and crisis in 2011, which was caused by downgrading USA credit ratings and European sovereign debt crisis. Nevertheless, our both solution outperformed the benchmark. Solution for 3 minutes reaching 5.4 and solution for 45 seconds reaching 4.1%. On this graph, we can see Sharpe Ratio. Sharpe Ratio is a measure of how efficiency is investment. It expresses the amount of return earned per unit of risk. We can see that the both of our solution also outperformed the benchmark, landing 105 and 79. Tracking error is a measure of how widely, of how we closely follow the benchmark. For solution 1, we have picking up solution which bit divides from the benchmark, picking its maximum at 7.2%, and for the other solution it's a bit passive, which result with a lower tracking error of 6.4%. There is several reasons why we choose up this approach. It can easily handle large-scale data. It has flexibility and efficiency of use in terms it gives the user possibility to incorporate new constraints or changing and delete the old ones and changing also the parameters. It gives a quality solution for a very reasonable amount of time. We saw that both of our solution now perform the benchmark. In the left corner we can see for the first solution of 3 minutes statistics, and it has one drawback. We have no proof of optimality, which exact methods gives, but to generate a solution for exact methods, it can take too much time, which nowadays managers might not have. For the future research, we would like to upgrade our heuristics with hybrid ones or even with parallel optimization. Regarding the bonus question, we would like to incorporate tools such as modularity maximization and models of stochastic programming, which would predict parameters like return and alpha. Okay, in this paper they were given, but in reality they are probability determined. In the end, I would like to thank you all for your attention, to thank our faculty of organizational sciences and our teacher from the Department of Mathematics and Operational Research, and my colleagues too. Thank you for your attention.